Hello everyone, and welcome to this video on sections 6.3/6.4. And in this video, I'm going to be taking you through just part of a Newton-Alta assignment for this particular group of sections. I'm only going to be going over the problems on the objective with the heading Taylor's Theorem with Remainder. So please understand that the questions that I see in this video may not be exactly the same as the questions that you see when you work on the assignment yourself. But hopefully the questions are similar enough and the way I do them is good enough to help you out when you work on the assignment yourself. All right, so here it is, Newton-Alta assignment page. In upper left-hand corner, you'll see the title without the word preview. Upper right-hand corner, you'll see your mastery bar, which shows you how far along you've gotten. So again, I'm not going to be finishing the assignment in this video. I'm just doing part of it, which you can see in the activity log next to this. So I've already done a video on the Taylor and Maclaurin series objective. Today, I'm doing the video on the second heading, Taylor's Theorem with Remainder. So the objective is, use Taylor's theorem with remainder to answer questions regarding the error of a Taylor or Maclaurin series. So you may recall, if you watched the first video or saw the first problems from the first objective, that we were using Taylor polynomials or Maclaurin polynomials to estimate a function value. Well, today we're going to see how to put bounds on the error, determine the error in these estimates. Then on your main page, then you got the current objective. Beneath that, a question related to that objective. At the bottom of every question, you should be seeing a feedback button. Right? So if you see any issues with the question itself, or maybe the answer explanations, or something, you can send feedback directly to Newton, and hopefully someone will get back to you and fix your issue. You will not have this instructor cheat button. This is for instructors only. But you will have a more instruction button. Right? So if you're struggling with a topic or a particular objective, click on this and you'll be taken to a place, a page with reading to do or videos to watch or both. And you'll be given questions related to that instruction that you can work on while the instruction is still up. And you can keep referring back to it. And you can work through the entire assignment this way using the more instruction anytime it comes up. All right. So like I said, the only objective in this video is going to be use Taylor's theorem with remainder to answer questions regarding the error of a Taylor or Maclaurin series. So first, let me bring up what is this Taylor's theorem with remainder, and then we'll apply it to our problems here. Okay, so hopefully you'll recall from last video what a Taylor series centered at x equals a was. I mean, I'll still write it up. Okay. So remember a Taylor series representing some function, say f of x, and centered at, x equals a, was the following. We had f of x equals the sum from n equals 0 to infinity, and then they had the coefficients of this Taylor polynomial, the power series, was f with a little n above it in parentheses. That was the value of the nth derivative of this function f, evaluated at a, right, at the center a, whatever the center value is, divided by n factorial, and then you had your powers of x minus a, right? All those are your coefficients times x minus a to the nth. Right? And of course, we'd have to say, that this series converges to this function at x for only certain values of x, right? So we'd have to also identify an interval of convergence and radius of convergence um, using the ratio test or something. You saw how to do that for a power series in the section 6.1 or 6.2 videos, those assignments. So we'd set up some series for a function and then also have to determine some interval and radius of convergence. So I'm just going to say with radius of convergence r, right? And again, that can be 0 if the series only converges at a, if it's not 0, but also not infinite, then the series would converge for values, from a minus r to a plus r, possibly at both ends. And of course, r could be infinite if the series converges for all real values of x. Now I can split this up to our Taylor polynomial. Remember the nth, again, remember this from the first video from the section 6364 on Taylor and Maclaurin polynomials. So we can split this up actually and make an estimate for f of x by going up to, say, capital N instead of to infinity. We use, again, what they called the nth Taylor polynomial. So I can say this is the sum from n equals 0 to capital N of these terms, right? Again, the nth derivative of a divided by n factorial times x minus a, to the nth. And you may recall the notation for this. This was our nth polynomial, p sub n of x. And that was used in the last video to approximate f at certain values of x. But then add to that, the rest of it. The sum from little n equals, this goes up to capital N here. So the next term in our infinite series would be capital N plus 1. So from little n equals, capital N plus 1 to infinity of these terms, and the nth derivative of a divided by n factorial times, x minus a to the nth. This this is called the remainder or the error in our approximation. Right, so again, this polynomial up to capital N here, this is what we're going to use to approximate f at x, and then the rest of it is the remainder, what's left over. How how far off of the actual value of f are we? So the remainder slash the error. Now, if we're approximating f with the nth, capital Nth Taylor polynomial, this is going to be denoted as the remainder after the capital Nth polynomial. So you'll see remainder sub capital N here, whatever degree we're going up to for the polynomial. You see remainder with that subscript of x. All right. Now, Taylor's theorem states the following. Now, this isn't going to be the full statement. I'm just going to write the key parts. All right. If you want to see the full statement and the proof of it, you can go to the more instruction in Newton Alta. They do have the statement of Taylor's theorem for remainder, and also a proof of it. And you'll see that the proof involves Rolle's theorem, which is, remember, a special case of the mean value theorem that you may have probably learned about, more than likely learned about in Calculus 1. Yeah, so again, I'm just going to write up the key parts. I'm not doing a proof or anything here. Right. So Taylor's theorem is that this R sub capital N at x, right? So if I'm approximating f of x, and this is the error, right? This is the remainder after the nth polynomial, when the nth polynomial is used to approximate f. Well, this should be equal, okay, to not just this big sum here. All right, yeah, this is correct here too, right? This is initially the remainder. But this sum is actually going to be equal to the value of the capital N plus 1. Right, so again, that's like having the first term here, n plus first derivative, but not at x, not at a. It could be at x or at a, but at c, really. Right? Now, they put the letter c here. Now, c, this value c mentioned here, and I'm not done, there's more to this, but this value c that's mentioned is between x and a, right? So remember, a is the center of our polynomial, right, where the power series is centered. And x is the value we're plugging in, and to our function and trying to approximate the value of f of x. So this, again, this comes from the the proof of this is, coming from Rolle's theorem, or the mean value theorem, which, remember, involves values between endpoints. I'm going to write it up again, like I said, and you can go to your OpenStax text or the more instruction here and see the proof. Divided by, capital N plus 1 factorial times your, x power of x minus a. It looks exactly like the first term of this sum, but with, instead of a here, you got some value c that's lying between x and a, and times x minus a to the capital N plus 1. Right. Now the rest of the statement, the important part is the following. So if, right, so if for any c between x and a, the absolute value of this n plus first derivative of the function at c is less than or equal to some value capital M. All right, so M is just some positive value, right? Absolute value, so this should be positive. if this is the case, if this n plus first derivative between x and a is always lower than a specific value, it's always under m, then we can put a bound on the absolute error in our approximation. Right, so then the absolute value of our remainder, right, the absolute error. So when we approximate f at x with the nth degree Taylor polynomial, this is how far off our estimate is, right? The absolute value, this is just the distance off. The absolute value of this r sub n of x. So is how far off our estimate is, right, is again the absolute value of this. That'd be the absolute value of this, but we just said, hey, if there's this m, that the absolute value of this derivative is always less than between x and a, then our absolute error is always less than or equal to this m, right, replacing that, over, now n plus 1 factorial will always be positive, so I don't need the absolute values around that. And then times, the absolute value of x minus a to the n plus 1 power, right? Because x minus a could be negative, so absolute value around that. And here we go. This is, we're going to be using this a lot throughout these problems. And what this gives us is a bound on the error. It gives us a bound on the error for our approximation. So again, as long as m is always larger, or always at least the value of the n plus first derivative for any value between x and a, we can make this statement. All right. So let's go and use this now. Oh, and by the way, if a is 0, remember if a is 0, they call all this stuff Maclaurin instead of Taylor. So you may recall that from the last video. Because notice in the first problem here, they ask us to determine the degree of the Maclaurin polynomial. So that just means Taylor polynomial, right, where a is 0, so centered at 0. So determine the degree of the Maclaurin polynomial of 2 cosine of x necessary to guarantee the error in the estimate of 2 cosine of 0.15 radians is less than 1,000th 0.001. So we're trying to determine, how many terms of our Maclaurin series, right, Taylor series centered at 0, how many terms do we need to approximate 2 times the cosine of 0.15 within 1,000th, right, and have an error no greater than 1,000th. All right. So let's see. So let me pull up, the function we're given here is 2 times the cosine of x. Right, 2 times the cosine of x. We're talking Maclaurin. Right, Maclaurin meaning a equals 0, right? That means the center is at 0. And our Maclaurin series, looks like this, sum from n equals 0 to infinity. And then I'm taking the value of all the derivatives at 0, divided by n factorial for the coefficients, and then times powers of x minus 0, so just x to the nth. So first, we have to try to determine a general rule here for these coefficients. All right, so it's a little more involved than the last video, right? The last video, we just went out to a certain degree, a certain power of x for a Taylor polynomial or a Maclaurin polynomial. So first here's f, right? Now f prime would be -2 times sine x. Second derivative be -2 cosine x. Third derivative be 2 sine x. And like you saw with the last video, and again probably in Calc 1, remember these multiples of sine or multiples of cosine repeat every 4 derivatives, right? The fourth derivative, I'll just put a little 4 in parentheses here, back to being, 2 cosine. So I'll just keep this in mind because I don't need to go to, the fifth derivative will be the same as the first. The sixth derivative will be the same as the second. The seventh derivative will be the same as the third. So I'm just going to keep these up and, just remember that they repeat. And for the Maclaurin series here, I'm evaluating all of these at 0, right, for these values of the nth derivatives at 0. So the 0th derivative, remember, is just the original function. At 0 would be 2 times the cosine of 0. That's just 2. Right? 2 times 1. And then what we're going to see is that all these odd derivatives at 0 are just 0. So all the odd powers, right, all the odd powers of my polynomial are going to be 0. Going to be nothing. No odd powers. Right? The value of the second derivative at 0 would be -2. The value of the third derivative at 0 is 0 again, right? Sine of 0 is 0. And then we just start over, right? These 2, 0, -2, 0 just keep repeating, right? Look at the value of the fourth derivative at 0 is back to 2 again. And again, these just keep repeating. All right. So this Maclaurin series for 2 cosine x looks like this. So I'm just going to kind of write out the first several terms of this. Be 2 plus nothing. The first powered term has a coefficient of 0. Then minus 2 over 2 factorial. Remember, second derivative over 2 factorial. I know that's just 1, but I'm going to leave it that way for right now. Because we're trying to find a general version of this, right? Times x squared. And then plus, no x to the third power, right? The third one, 0. And then we start over. So plus 2 over 4 factorial, right, for the x to the fourth term. And then I keep repeating this with all the even powers. Again, all the odd powers would have a coefficient of 0. So we'd have minus 2 over 6 factorial times x to the sixth, plus 2 over 8 factorial times x to the eighth, and so on. And hopefully you get enough out here where you see a generalization. All right. So in general here, the value of the and because all the, I'm going to do this. because the only powers that are showing up are even, right? Only even powers are showing up in non-zero terms in this. I'm going to represent that. Say that, f sub the even derivative, right? The value of an even derivative at 0. Well, the way they represent even numbers quite often is just as a multiple of 2. Remember, every even number is a multiple of 2. So maybe I do 2k here, or 2n, whatever. That's an even number, where k is an integer, right? Where k is equal to 0, 1, 2, blah, blah, blah. 2 times 0 would be the 0th, and then the second for k equals 1, fourth for k equals 2, and so on. And so what we see here is that, the value of the 0th derivative was positive 2, the second derivative was negative 2, the fourth positive, negative, positive, negative. So I should have this power of negative 1 going on, and it's to the k, right? Because when k was 0, it should be positive. K is 1 for the second derivative, it would be negative, negative 1 to the first. And this will alternate. And then we had times, 2. This was alternating 2's. And then for the coefficients in our polynomial, right, we just divide by the value of that derivative, factorial. That's 2, so whatever 2k is factorial. And then again, so basically up here, I'm replacing all my n's with 2k, and I'll just replace n with k. Right? So here's the Maclaurin series, the whole thing for this function. So 2 cosine x, I can express as the sum. Now, if you don't like n being k, I can call these k's n again. Just have it be like we're used to, sum from n equals 0 to infinity. But just use even stuff, right? Just the value of just the even derivative over the even factorials, because all the odd stuff went away. So we have negative 1 to the k, right, times 2 over 2k, 2, oh, sorry, I just said you can use n. So negative 1 to the n times 2 over 2n factorial, and then times x to the 2n. Again, I just want to use all the even stuff. And you can double check that this actually matches what I've written up here, right? When n equals 0, you'd have 1 times 2 over 0 factorial times x to the 0, that's just 2. And when n equals 1, you'd have negative 1 times 2, so negative 2 over 2 factorial, right? Negative 2 over 2 factorial times x squared. And you see that it's matching what we had written up earlier. Okay, so there's the Maclaurin series for this function. And then something you're also going to have to do, not in this video, okay, but we haven't gotten to the error part yet. I just wanted to show you how to develop a Maclaurin series at least, because it's important. Then we would also, once we've established the power series, okay, once you've established the series that represents the function, you would also have to find an interval of convergence. You would also have to find the interval and radius of convergence. Now, for what values of x will this infinite series actually converge to 2 times the cosine of x? All right, so that'll involve, doing that ratio limit from the ratio test. So suppose I called these terms we were adding up, a sub n. All right, there's some sequence a sub n. And then I would do this ratio limit. Right? Remember the ratio test, we're taking the limit. It then goes to infinity of the absolute value, because again, it was a test for absolute convergence. And if a series was absolutely convergent, like the original was convergent, of a sub, n plus 1 over a sub n. Well, for this here, and I'm just going to get rid of this power of -1 to do an absolute value. So I'm just going to make these all positive here and just get rid of this -1 to the nth. So this would be the limit as n approaches infinity of the absolute value of, 2 times x. Now that'd be 2n plus 2. If I replaced n with the quantity n plus 1 and distributed the 2, I'd have 2n plus 2 power there. And then same thing for the factorial. I'd have 2n plus 2 factorial. And then times the reciprocal of this, right, divided by what the a sub n, which would have, 2n factorial in the numerator, and then this 2 times x to the 2n in the denominator. And what we'd end up with, you'd have x squared, which I can pull out because it doesn't have n involved, right? Anything that's not n is constant. So you can pull out the absolute value of x squared, or just x squared, because that'll never be negative, times the limit as n goes to infinity of the absolute value of, now the 2's cancel, and then 2n plus 2 factorial, that'd be 2n plus 2 times 2n plus 1 times 2n factorial. So the 2n factorials would go away, and I'd be left with 1 over 2n plus 2 times 2n plus 1. And this limit is 0, right? The denominator will be getting huge as n gets infinite, and the numerator is always 1. So no matter what x is, this is less than 1. This limit is 0, which is less than 1 for any value of x. So our series up here converges, right? This series converges to this function for any value of x, right? So this is for x between, negative infinity to infinity. The radius of convergence then would be considered, infinite. But yeah, you should have to do this, right? You should do this every time you have a power series, an infinite series, right? You should be trying to determine, well, yeah, I've got this infinite series representing this function, but is it always equal to this function? Where is it equal to this function? You got to find that, right? Find the interval of convergence. Well, now that I know this series converges to this value, no matter what x is, I can use, parts of this series. I can use Maclaurin polynomials to approximate this for any value of x. All right, so it makes sense to plug in 0.15 here, or anything. Now, if I had a value now if there was an interval of convergence that was smaller, and then they asked me to use the Maclaurin series to approximate something outside that interval of convergence, with a value of x outside of the interval of convergence, it wouldn't make any sense. Right? It only makes sense when the value we're using, is actually part of the interval of convergence, which here every value is. All right, so now, okay, uh, to the error. The remainder term, the r sub n, right, I was using capital N. Remember, this is if I add up, go from n equals 0 to capital N of this, right, this series here. when is the error in my approximation going to be less than 1,000th, right? And remember, we're trying to approximate 2 times the cosine of 0.15. So that would be f, at 0.15. So this 0.15 is the value of x we're talking about. And remember, the value of a is 0. We're centered at 0. Now this nth error term, right, is the value of the n plus first derivative of this function, right, 2 cosine x, at some c, this was written up earlier, where c is between 0 and 0.15, right? C would have to be some value between 0 and 0.15. Divided by n plus 1 factorial, and then times, x to the n plus 1. Now we're going to replace x with 0.15 here in a second. Again, a was 0, so that's why this is just x to the n plus 1. Now let's look at the absolute error, right? How far off our estimate is from the actual value. So remember, the absolute error is just, again, how far off the estimate is from the actual value. That's absolute value of this r sub n of x, which is, the absolute value of this n plus first derivative at some value c between 0 and 0.15, divided by, capital N plus 1 factorial, and then times the absolute value of x to the capital N plus 1. Again, we're going to replace x with 0.15 in a minute. What I'm concerned with is this absolute value of the n plus first derivative. What is a bound on this? Well, if you look at all the derivatives, we were doing derivatives of this earlier. Right? All the derivatives of this function are some multiple of, sine x, 2 sine x or 2 cosine x. Right? So when I look at all the derivatives, right, so like, the n plus first derivative of this function, and then look at the absolute value. Look at my absolute value here. And if I did the absolute value of every single one of these, it would be 2 cosine x, 2 sine x, 2 cosine x, absolute value of sine x, absolute value of cosine x, whatever. So this is always going to be equal to 2 times, the absolute value of, well, I guess I should split this up because there's 2 possibilities. So for, odd derivatives were multiples of sine, even derivatives were multiples of cosine, 2 times cosine. So here, to have this be even, n would be odd, right? Odd plus 1 is even. So when n is odd, we're getting 2 times the absolute value of cosine. And when n is even, right, that would give me an odd derivative, and all the odd derivatives had multiples, 2 times the absolute value of sine. Right? But no matter how you slice it, remember the absolute value of cosine, absolute value of sine, are always less than or equal to 1, right? Always less than or equal to 1. That was something you may recall or remember from a trig class, right? When you first learned about sine and cosine. So this here is less than or equal to 2 for any x, not just x's between, not just values between 0 and 0.5, but for any, c between 0 and 0.15, but for any x, especially between these two. Right? So that's going to be my bound, right? This error is less than or equal to 2, right? This absolute value of the derivative thing is less than or equal to 2 over n plus 1 factorial times x, the absolute value of x to the n plus 1. All right, so now specifically for x equals 0.15, right, we get the following. So for x equals 0.15, right, the absolute error of our estimate at 0.15 should be less than or equal to 2 over n plus 1 factorial times, and then the absolute value of 0.15 is 0.15, right? So times 0.15 to the n plus 1 power. And they said, right, so our error is going to always be less than whatever this value is when we go out to the nth polynomial, right? The nth polynomial estimate for the function value. And we need this to be less, right? They said we want this to be less than 0.001. Right, so I'm going to go to a calculator and see when is this happening. For what values of capital N is this happening? And that'll tell me how far I need to go to make the estimate with that level of accuracy. All right, so I'm going to go to Desmos. And I'm going to enter that expression for our error bound. 2 over, capital N plus 1 factorial. And then we had multiplied by 0.15, to the capital N plus 1 power. And then add a thing for n, and I'm just going to now see when n equals 1, the error would be, you'd be off by less than this. You'd be off by less than 0.2, but that's not less than 1,000th. 0.02 is not less than 0.001. So I just keep increasing the value of n here. Still, when n equals 2, this is not less than 0.001. So I'm thinking 3, you'll do it. Yeah, look at that. When n equals 3, this error bound is 0.00004, which is definitely less than 1,000th. So when I go out to the third degree Maclaurin polynomial and use it to estimate 2 times the cosine of 0.15, we're guaranteed the error to be less than this, which is, again, definitely less than 1,000. So 3 is the answer. So back here, put in 3. And let's just double check too, right, before I submit the answer. So remember, 3 is my answer, right? 3, 3, 3. So back to paper. So this happens for capital N greater than or equal to 3, right? Again, when n is 3 or greater, this will happen. You'll have an error less than 1,000 for sure. Well, let's see that. What is the third Maclaurin polynomial? Maclaurin polynomial, Taylor polynomials. So remember, that's the sum from n equals 0 to 3. Right, we're just going out to the third powered term here. Right. Now you're going to see that the third powered term will pretty much be just the same as our second powered term, right? Because remember, this is the value of the nth derivative at 0 divided by n plus 1, divided by n factorial, and then times x to the nth. And we saw a bunch of these derivatives at 0 earlier. Remember, the 0th derivative at 0 was 2. The first derivative at 0 was 0. Then the second derivative was -2, right? So minus 2 over 2 factorial, so that'd be minus 1x squared. And then the third, when n equals 3, you got 0 again. So there's P3. P3 is actually the same as P2. But this, right, and this is approximately equal to, 2 cosine x. And according to our statement up here, this should have an error less than 1,000 when I plug in 0.15. So let me type this in, show you. So again, our function, right, f of x was 2 cosine x, and I'm in radian mode. You can see the wavy thing there. And then the polynomial we're using, the Maclaurin polynomial 2 minus x squared. And you see how that, around 0 here, because remember Maclaurin's centered at 0. Let me bold this up. See how that's, when we're centered at 0, see the polynomial 2 minus x squared pretty well matches. It's pretty close to the graph of the 2 cosine x. Right? It's just, the further away from 0 I get, the worse off it is. I'd have to add more and more terms on to get better approximations further away from 0. Now look at f of 0.15. All right, so there is the actual value of 2 times the cosine of 0.15, 1.9775 something. Now look at p of 0.15, and you see how these are the same to the first 4 decimal places, right? It's definitely less than 1,000th. Right? If you subtracted these, you'd get a value, less than 0.001, right? F of 0.15 minus the polynomial at 0.15. There's the error. And you see the error is definitely smaller than 1,000th. Now here's my issue. So I'm going to do this. Yeah, so all right. So they see, I remember I said, because the third polynomial is exactly the same as the second polynomial, we can use 2 instead of 3. And that's exactly what happened. I just wanted to make sure that they were saying the same thing. So you see n equals 2. Now in my error estimate, you need to go out to 3 for this expression. But in the polynomial, right, the Maclaurin polynomial, the third term is 0. So really I only need to go out to the second term. All right, I know that can be a bit confusing, but you'll see that a lot for sine and cosine. I guess something else we could have done, but this is a bit involved, is we set our n plus first derivative where this and this, 2 cosine, absolute value of 2 cosine x, 2 absolute value of sine x. Now between 0 and 0.15, yeah, the maximum of this is 2, right? Because 2 cosine 0 would be 1, or it would be 2, and 2 times sine of 0.15 would be smaller. Yeah, they're using the fact that P3 is the same as P2 to say, okay, 3 works, but because P3 is the same as P2, we only need to go out to the second degree polynomial here. And that's the degree of the polynomial. Okay. So they didn't say what level they asked for the degree, right? And P3 has degree 2, right? This is a degree 2 polynomial. Okay. So that's another valid reason to say why the answer is 2 here. Right. Again, after every answer, you are given some sort of answer explanation. Please read through these. If you're correct, read through it to make sure you got it right for the right reasons. And if you're incorrect, make sure you read through it and figure out why you were correct. Let's see if I read through here. Have our So they have the whole 2 over n plus 1 factorial times 0.15 to the n plus 1. Okay, so we got that there. Oh, I see what happened. They didn't do the general. Okay. So they weren't doing the general like I was. All right, so I actually did a much more involved answer than needed. So they took it one step at a time. I did it in general because, I don't taking it one step at a time. What if it took out to the 100th term, to get an error less than 1,000th? I wouldn't want to do it one step at a time if it took me if I needed to go out to the 100th term. So see how they're doing it. They're checking for, one first, nope, and then when n equals 1, this derivative, the n plus first derivative is less than or equal to 2. But when n equals 2, the n plus first derivative is always less than 2 sine of 0.15. So they're using that as the bound, and that's less than 1,000. So that's why they got 2 there. Okay. I don't particularly care for the fact that this is used, right? Because, we're trying to estimate 2 times the cosine of 0.15. Chances are, if you don't know what 2 times the cosine of 0.15 is, then you don't know what 2 times the sine of 0.15 is. So why would you use something that you haven't even estimated yet or you don't know the value of in a calculation? So I still got a correct answer. It's just I now know how they're approaching it. So like I said, even if you got it right, read through them because, they may do something that you want to do for future problems. You might see, the way they want things done. So I'm going to keep this in mind for questions after this. So here we're asked to determine the interval of convergence for the Taylor series of e to the 8x power, centered at x equals 8. Write your answer in interval notation. So again, I'm making a Taylor series. So this is like the last problem where, I made the Maclaurin series for 2 times cosine x, right? I tried to find a general formula for it, for each coefficient. So here we're given f of x equals, e to the 8x power. And we want a Taylor series centered at x equals 8, or a equals 8. The value of a is 8. So every single term is going to have a power of, x minus 8 involved. That's this series here. The sum from n equals 0 to infinity of the value of, each derivative at 8. Right? Remember the value at the center divided by n factorial, times x minus 8 to the nth. So yeah, so I'm going to try to find a little general formula here for the nth derivative at 8 divided by n factorial. Right. Now the nice thing is all these derivatives are good, are easy. Right, the first derivative would be e to the 8x, times 8 to the first using chain rule. The second derivative would be 8 times e to the 8x, and then times 8 again, so that'll make this 64, or 8 squared. I'm going to leave it that way for a reason. The third derivative would be 8 cubed times e to the 8x. So I'm hoping to see that the general, nth derivative here would just be 8 to the nth power times e to the 8x. Right? And what we want in our formula here is the value of the nth derivative at 8. Right? So the value of all of these at 8, at x equals 8, would be whatever 8 to the nth power is times e to the 64th power. Right? E to the 8 times 8. So I'm going to put this into my series here. And here we go. Here's the series for e to the 8x, centered at x equals 8. So it'd be the sum from n equals 0 to infinity of, and then we just saw, the value of the nth derivative at 8 is this. So 8 to the nth times e to the 64th divided by n factorial, and then times, x minus 8 to the nth. There's our Taylor series for this function. Now they're asking us, right, for the interval of convergence. So that's like I did in the last problem, right? You need to find the interval of convergence using the ratio, that ratio limit, right, from the ratio test. I'm going to call this, all the terms of our series here, a sub n. We're taking that following ratio limit, right? What's the limit? As n approaches infinity of, the n absolute value of the n plus first term divided by the nth term, right? Every term divided by the term before it. So that's this. Now if I replace all the n's with n plus 1, this is going to be 8 to the n plus 1 times e to the 64th divided by n plus 1 factorial times x minus 8 to the n plus 1. Now that's actually in the numerator, x minus 8 to the n plus 1. Sorry that that's tiny. And then we're dividing by this, dividing by a sub n, which is multiplied by the reciprocal of this. So times, n factorial over 8 to the nth e to the 64th times x minus 8 to the nth. All right, sorry about that. The absolute value, that was tight. So this would be the limit as n approaches infinity. Now a bunch of stuff is going to cancel here. You got e to the 64th going away. There'll be just 8 left over in the numerator. All right, 8 to the n plus 1 over 8 to the nth. There's going to be n plus 1 left over in the denominator because n plus 1 factorial is n plus 1 times n factorial. That'll cancel the n factorial. And then I'll have x minus 8 in the numerator, right? So just x minus 8. Right, and this will be this absolute value of x minus 8 can come out, right? That doesn't involve n at all, so it's considered constant. Times the limit as n approaches infinity of, 8 over n plus 1. And this is going to 0 again. All right, 8 over n plus 1 as n goes to infinity, the denominator will be getting huge, so this will be getting really small. This is going to 0, no matter what x is, right, for any x. And so this is less than 1 for any x, meaning the interval of convergence, right, so this converges for negative infinity to infinity, right? X can be any real number, and that's what I'm putting, right, the interval notation from negative infinity to infinity. So parentheses, right, negative infinity, comma, infinity, parentheses, right? And again, they take you through it. Same procedure I kind of just went through. Right? Great. All right, so this is just a yes or no question, right? But don't guess. Remember, don't guess, even though you get a 50-50 shot. If you get it wrong, right, that they just make the assignment that much longer. So here, does Taylor's theorem with remainder guarantee that the fourth Taylor polynomial of this function here at x equals 1, so centered at x equals 1, has an error less than 1/10,000th 0.0001 when you're estimating the 5 times the cosine of 1.5. All right. So based on what I saw in the answer explanations of the first problem, here's how we can approach this one. Right. So here's our function. Right? F of x equals 5 times the cosine of x. And we would like the fourth Taylor polynomial at x equals 1, centered at x equals 1. So that's the value of a, right, where the thing is centered. The a is 1. Now the fourth Taylor polynomial, right, P4 of x, remember that's just the sum from n equals 0 to 4 of the value of all the derivatives at a, right, so at 1, divided by n factorial, times, and then x minus a, x minus 1 to the n. So I need all these values here up to 4. Right, so we need up to the fourth derivative again. So first derivative is, negative 5 sine x. Second derivative is negative 5 cosine x. Third derivative is 5 sine x, and just like we saw before, the fourth derivative is the same as the first, or the original, from the 0th derivative. Fourth derivative is 5 cosine x. So if I evaluate all these at 1, right, we'd have 5 cosine of 1. So I'll write this out. So this fourth degree polynomial here would be, 5 cosine of 1, then minus, 5 times the sine of 1 times x minus 1, then minus 5 times the cosine of 1 over 2, right, over 2 factorial, times x minus 1 squared, then plus 5 times the sine of 1 over 3 factorial, over 6, times x minus 1 cubed, and then finally plus 5 times the cosine of 1 divided by 4 factorial, right, 24, times x minus 1 to the fourth, right? So there's our fourth degree, or fourth Taylor polynomial here, centered at 1. And remember, this should be approximately equal to our function, 5 times the cosine of x. Now they're asking us to approximate, right? We are approximating 5 times the cosine of 1.5. All right. So that's the value of x. Right, x equals 1.5. The value of a is 1. And this should be approximately equal to, the value of this P4 thing here, right? The fourth polynomial, the fourth Taylor polynomial at 1.5, if I were to plug 1.5 in for all these x's here. Now, they don't ask us to actually do this, right? This was in the last video. What they ask us for is when I do approximate this value with this polynomial, is the error guaranteed to be less than 1/10,000th? All right, so remember the error term. All right, so R4, right, R4 of x would be equal to, the value of the fifth derivative, right, at some value c, right, where c is between, remember, it's between x and a, so between 1 and 1.5, right? The center was 1. So between 1 and 1.5 is this value c here, right, divided by 5 factorial, right, so 120, and then times, x minus a, x minus 1, to the fifth power, and we'll plug in 1.5 for x in a second. All right, so let's look at the fifth derivative. Right, the fifth derivative is, the same as the first derivative, -5 sine x. Now, if you look at the graph of this, between 1 and 1.5 radians, so there's 1 and 1.5. Now, pi over 2 is 1.57 something. So 1.5 is a little left of pi over 2. And then, -5 sine x looks like this. Well, actually, we're going to be doing the absolute value of this, remember, so I want to do the absolute error, right, how far off we are. So we're doing the absolute value of this. So that'd be 5 times the absolute value of sine of x, which between 0 and pi over 2, the sine of x is positive anyway. So we'll have this, this graph, the graph of this absolute value of the fifth derivative would do this. Start off at 0, and then at pi over 2, it goes up to 5, but it's not getting all that way up, right? We're going here to here. There's from 0 to pi over 2, we're only concerned with between 1 radian and 1.5 radians, right? Only this part of the graph here. And the highest value in this region is, 5 times the sine of 1.5. So that's our bound, right? This is going to be less than or equal to 5 times the sine of 1.5 for values of x between 1 and 1.5, right? Which this value c is between, right? So this remainder, when we estimate that value at the fourth, with the fourth polynomial, when I plug in 1.5 for x, should be less than or equal to, this value of the fifth derivative is always less than this, right? So 5 times the sine of 1.5 divided by 5 factorial, right, divided by 120 times, and then 1.5 minus 1 is 0.5, to the fifth. Now I'm going to go to a calculator and calculate this here, and hopefully that, now we'll see if the error is less than 10,000th. Right. Back to Desmos. These are from our earlier problem. So we have 5 times the sine of 1.5 divided by 5 factorial is 120, then times 0.5, to the fifth. That is not less than a 10,000. That is not less than 1.0001. It's not even less than 1,000th. Right? So the answer is no. No. When we use the fourth degree Taylor polynomial centered at 1, that polynomial does not estimate this value within 1/10,000th. Now we can see what it actually does. All right, so I'm going to do this here. All right, our function, again, was 5 cosine of x. And then that polynomial, right, now this is going to take a bit, but for that fourth Taylor polynomial was this, right? 5 times the cosine of 1 minus 5 times the sine of 1 times x minus 1, then minus 5 times the cosine of 1 divided by 2 times x minus 1 squared plus 5 times the sine of 1 over 3 factorial, right, over 6 times x minus 1 cubed. And then finally, plus 5 times the cosine of 1 divided by 4 factorial, 24, times x minus 1 to the 4th power. Now you can see when I'm centered at 1 here, right, the graph of this black curve, the polynomial, is very close to the purple curve, right, our original function. We're trying to see how far off that is. Now, the value of f at 1.5, right? When I actually plug in 1.5 for f, there's 5 times the cosine of 1.5. It's 0.3536 something. Now, plug in 1.5 to our polynomial, and you see it's only good to the first 2 decimal places, right? Their error, right, if I subtract them, f at 1.5 minus the polynomial at 1.5, you see the error. Oh, and do the absolute value, I guess. So just make this positive. We're doing absolute value, right? Just how far off is the estimate? It's off by 0.001, right? Definitely not less than 1/10,000. So again, the answer is no. The error is not guaranteed to be less than 1/10,000. Right. And again, read through the answer explanations. I'm pretty sure, like I said, they're using that sign of, yeah, C5 sine 1.5. Again, I don't really care for that so much because, again, if you don't know the cosine of 1.5, you're trying to estimate that. How could you use the sine of 1.5, right? I don't understand that, but we got a calculator, so I guess they're just saying, hey, you can use a calculator, All right. All right. So here is suppose you are estimating the cube root of 5 using the second Taylor polynomial for the cube root of x at x equals 4. So use Taylor's theorem for remainders to bound the error, right? The error will be less than or equal to some value when you use the second Taylor polynomial to estimate the cube root of 5. All right, so I'm going to do that. I'm going to make the second Taylor. Now, you don't have to make the second Taylor polynomial. You can just go to the second remainder thing, so I'll show you. All right. If you want, you could make the second Taylor polynomial and try to estimate, cube root of 5 and see how far off you are and stuff. But so the function we're talking about here is, the cube root of x. Now I'm going to write that as x to the 1/3 power because I'm going to be doing a lot of derivatives. And we're talking Taylor at x equals 4, right? So the second, if I were to make the second Taylor polynomial, right, that would be the sum from n equals 0 to 2, and then the value of all the derivatives of this function at 4, right, divided by n factorial, and then times powers of x minus 4. Right? So that would be the second Taylor polynomial. Now the remainder, after the second Taylor polynomial, right? There's R2 of x. Remember, it's this. It's equal to the value of the third derivative at some value c. Now, the center is at 4, so that'll be a equals 4. And what we're trying to estimate is the cube root. They're saying estimate the cube root of 5. That would be f of 5. The value is 5 here for x. So when I talk about this second remainder term, the remainder after the second Taylor polynomial, this value c here is between 4 and 5. Right, it's got to be between 4 and 5. So this second remainder, right, the remainder after the second Taylor polynomial is the third derivative at some value between 4 and 5 divided by 3 factorial, right, divided by 6 times x minus 4 to the third power. And again, we'll replace x with 5 in a second. Now, I need to go down to the third derivative if I want to determine the bound for this error. Is that what value would this error always be less than or equal to when I take the absolute value, when I do absolute error? Right, so first derivative, I'm just using power rule a bunch, right? It's be 1/3 times x to the negative 2/3. Second derivative be negative 2/9 times x to the negative 5/3. And then the third derivative be positive 10/27 times x to the negative 8/3. Right. Now you can think of this as 10 over 27, and then x to the positive 8/3. That's x to the 2 2/3. So x squared times the cube root of x squared, right? That's x to the 2 2/3 power. Now, if we're doing absolute value, I mean, this is going to be all positive anyway because you got x squared, so I don't really need the absolute values around here. But the graph of this, right, the graph of this derivative between 4 and 5, this would definitely be a decreasing function. As x gets larger, the denominator would get larger, so this thing's getting smaller. All right, so if you're talking just over 4 to 5, it would be doing something like that. I don't know exactly what the values are, but I know it's got to be decreasing. All right, as x gets larger, the output would get smaller. So in this interval, right, between 4 and 5, the value of this third derivative is always less than the value at 4. All right, here's f triple prime at 4. We'll do absolute value, but it's going to be positive anyway. So that would be less than or equal to, so on this interval from 4 to 5, right, on the interval from 4 to 5, the absolute value of the third derivative on that interval is always less than or equal to 10/27 times 4 to the negative 8/3. I'll just put it in that way. So for our error, the error at, when I'm plugging in 5, when I'm estimating the cube root of 5, should be less than or equal to, this 10/27 times 4 to the negative 8/3. And then this is divided by 3 factorial, right? Divided by 6. I'll punch all this into some calculator. And then x equals 5, right? We're estimating cube root of 5. So 5 minus 4 to the third, that's just 1 to the third. So really no need to type that. And then they want us to round this thing here to 6 decimal places. All right. So back here, previous problem stuff. All right, so let's put that expression in. I had, 10/27 times 4 to the negative 8/3 power. All right, so there's that value, and then this gets divided by 6, and that's it, right? And times 1. All right, so the error when we use the second Taylor polynomial, to estimate the cube root of 5, it's going to be off of the actual value of the cube root of 5 by no more than this. So the first 2 decimal places will be correct for sure. We're guaranteed that. Yeah, so 0.001531 will be a bound on the error. 0.001531. And that's all we're asked to do, right? We're not actually asked to make the second degree Taylor polynomial and estimate it. Right? Right. Okay. So another one where we're asked to determine the interval of convergence for a given Taylor series, centered at x equals 1. Right? For this function, negative 14 over x at x equals 1. And of course, write your answer in interval notation. Now, this function we're given is one of them rational functions, right? Polynomial over polynomial here. And I see how to rewrite this in a way where we can use a geometric series. All right, but I'll do that real quick for you. And then we'll go through the Taylor series thing. All right. But still, like, you might recall, this has been brought up in the sections, 6.1, 6.2 videos, that if I have 1 over 1 minus something, I'll put a little block there, this can be written as a power series, right? The sum from n equals 0 to infinity of whatever's in that block to the nth power. But that's only when whatever's in the block is between -1 and 1. So if I want the series to be centered at 1, I want the block to have x minus 1 or 1 minus x in it, right? If I want this to be a series centered at 1, I need whatever's in the block here to be have x minus 1 or 1 minus x. Now our function is this, negative 14 over x, which I can think of this way as negative 14 times 1 over, and then if I want x minus 1 to be involved here, I subtract 1 and add 1. So I'll have, x minus 1 plus 1, then rewrite some things down here so I get 1 minus something. All right, so this is negative 14 times 1 over, and then I'll put this 1 in front, and then factor out a negative 1 from this, minus the quantity 1 minus x. All right, that's 1 minus 1 is 0, and then plus x will be x. So this function here is exactly the same as that one. And now you see the expression in the block is 1 minus x or x minus, it's something that's going to give me a center of 1 when I write it as a power series. So as a series, this should be equal to negative 14, all right, times the sum from n equals 0 to infinity of this, 1 minus x to the nth. Which, if I factor a negative 1 out of this, you'd have negative 1 to the nth times x minus 1 to the nth, and then I'll put the negative 14 in. So that'll be the sum from n equals 0 to infinity. Now, the negative 14, you can think of that as negative 1 times 14, and then there's a negative 1 to the nth here. So I'd have 14 times negative 1 to the n plus 1, and then times x minus 1 to the nth, right? So there's your series representing our function. But this is only for when the thing in the block, right, 1 minus x, is between negative 1 and 1. And if you solve for x, right, subtract 1 from everything, and then multiply everything by -1, that'll flip everything. X has got to be between 0 and 2, right? There's the interval of convergence from 0 to 2, right? So there's a series centered at 1. This would be called, any power series is some kind of Taylor series, a Maclaurin series for some function. Centered at 1, right? And all converted from 0 to 2 here. I've got the answer, and I didn't have to do derivatives or anything. But still, let's go about it using that Taylor series stuff, right? So this is -14 over x, which I'm going to think of as -14 times x to the -1, right, just for derivative purposes. We're asked to make this Taylor series, centered at x equals 1. All right, so the sum from n equals 0 to infinity of the value of the nth derivative at 1, right, at the center, divided by n factorial, and then times powers of x minus 1. Right, so same as any other Taylor series. So what I'm going to do is I'm going to try to figure out a general formula here for the nth derivative. All right, so the first derivative be, positive 14 times x to the -2. Second derivative be, now I'm going to do this, -14 times 2, you'll see why in a second, times x to the -3. And then the third derivative be positive 14 times 3 times 2 times x to the -4. And I'll do one more and hopefully we can see it. Well, hopefully you can see it. I mean, I can see it already, but like this would be negative, 14 times 4 times 3 times 2, and then x to the -5th and blah, blah, blah. So what we're seeing here is that the nth derivative of this function, well, it's going to be alternating, right? So I need some power of -1 here. Right? So -1 to the something. And I want it so that when we have an even derivative, it's negative, and we have an odd derivative, it's positive. So that's got to be n plus 1 power, right? N plus 1, n minus 1. Right, that way when n is even, you get -1 to an odd, which will make it negative. So even derivatives will have negative coefficients, and when n is even, or when n is odd, you'll get -1 to an even. So it'll be a positive coefficient. Times 14, right? Notice all these have this 14 in common. And then you have the factorial after it. 4 factorial, 3 factorial, 2 factorial. 1 factorial is 1, 0 factorial is 1. Right? So times, the fourth derivative had 4 factorial, third derivative had 3 factorial, so the nth derivative should have n factorial here. And then times x to the opposite of whatever n plus 1 is, right? The -5, 1 higher than the derivative. Now when I plug 1 into this, that'll just make this 1 to a power go away. So the value of every derivative at 1, right, which is what we need for our Taylor series, is just this, -1 to the n plus 1 times 14 times n factorial. And then don't forget for our coefficients, this value of every derivative at 1 is going to divide by n factorial. If I divide by n factorial, that'll make the n factorials disappear, and we get the following series, right? So our function here, -14 over x, is the sum from n equals 0 to infinity, and then this nth derivative at 1 divided by n factorial we saw is just -1 to the n plus 1 times 14, and then times your powers of x minus 1, right? Times x minus 1 to the nth. And isn't this exactly the same series I got when I looked at it as a geometric series on the last page, right? Look at that. I mean, I had the 14 and the -1 to the n plus 1 in a different order, but it's the same series. And then you would have to go about using that ratio test, to find the interval of convergence, right? So again, I call this a sub n, and we'll take, now because I'm doing absolute value, I'm going to ignore the -1 to the n plus 1 thing. This is a test for absolute convergence, right, the ratio test. So we're doing the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. All right, now I'm hoping you can see that. I'll just write it. I can't assume that you're going to see that. Now again, I'm not going to write the -1 stuff. That'll be gone. We're doing absolute value. So the numerator is going to be 14 times x minus 1 to the n plus 1. The denominator is going to be 14 times x minus 1 to just the nth. And so I'm left with just the absolute value of x minus 1. That's it. And we're asking, when is this less than 1? Well, that'll be less than 1 when x minus 1 is between -1 and 1, or when x is between 0 and 2. There's values that this series will converge for, which is, again, we saw this on the previous page when I looked at it as a geometric series. But the thing about this is, though, I didn't know that this was some geometric series, so I have to check the ends here. Don't forget, when you use this ratio limit, you have to check the ends, because at the ends, when x equals 0, when x equals 2, this limit is 1. Remember, the ratio test was inconclusive when the limit was 1. So I got to check the ends. So when x equals 0, here's what our sum looks like. Got the sum from n equals 0 to infinity of -1 to the n plus 1 times 14. And then now when x equals 0, this becomes -1 to the nth. And I can pull the 14 out of this. And then we'd have -1 to the 2n plus 1 power. That's always going to be -1, right? That's -1 to an odd, right? That's always -1. So this is the sum, 14 times the sum of just -1. So this is like having 14 times, -1 plus -1 plus -1 plus -1 forever, right? Definitely divergent. All right, so 0 is not included. And then when x equals 2 at the other end, all right, the sum looks like this. And then when x equals 2, this becomes 1 to the nth, so just 1. So you're getting this sum. And this is just an alternating sum of 14s, you'd have 14 minus 14 plus 14 minus 14 plus 14. This is divergent. We've seen something like this in earlier sections. Right? The sum is not going to anything. It's the partial sums would be 14, then 0, then 14, then 0, then 14. Right? The sum is not actually approaching some specific value. So divergent at both ends. This is it. Right? 0 to 2, interval notation, 0, 2 with the parentheses around it. That's the interval of notation, or the interval of convergence for this series, written in interval notation. So back in the assignment, right, 0, 2, and submit. Okay, looks like we still got more. All right, so this is another one of these where this is like the very first problem we saw in this video. So this time I'm going to do it the way that was laid out in the answer explanations from that first problem, where we'll take it one term at a time, one step at a time, all right, until we get the degree of the Maclaurin polynomial necessary for the error of the estimate f of 0.21 to be less than 1,000th, when f is, this. Actually, though, because this isn't sine or cosine, not really going to switch up on me. Because, when I had the sine and cosine ones, that switched on me, every even derivative or odd derivative. Because remember, there were two possibilities. Go back to that first problem with 2 times, I think it was 2 times the cosine of x. Remember that n plus first derivative? There were two possibilities, right? Depending on if n was even or if n was odd. That won't be the case here. So you know what? I'm going to approach this the same way I did that first problem, actually, because it won't be switching up on me. So here's our function. F of x equals, 13 times the natural log of x plus 1. We're asked to approximate, well, we're not asked to approximate, though. We're asked to figure out what degree Maclaurin polynomial should we use to approximate, this at x equals 0.21. Approximate this, f of 0.21, and that would be 13 times the natural log of 1.21. With a Maclaurin polynomial. Right, so again, Maclaurin means the center is 0. So a is 0, and then the value of x is 0.21. All right, so that means, when I write up the little error term later, right, that remainder term, there's going to be this value of c showing up, and c is going to be some value between 0 and 0.21. Right. So what I want to do here is try to figure out a rule for the general derivative. So remember, the first derivative would be 13 over x plus 1, or, 13 times x plus 1 to the negative 1. And then this is going to be pretty similar to the last problem, the 14 over x, right? Because you have powers of, x to the negative 1 here. You're going to see. Right? So second derivative be negative, 13 times x plus 1 to the negative 2. Third derivative be positive 13 times 2 times x plus 1 to the negative 3. And fourth derivative be negative 13 times 3 times 2 times x plus 1 to the negative 4. And I'll just do the fifth derivative. Why not? But hopefully you see a pattern here. Be positive, 13 times 4 times 3 times 2 times x plus 1 to the negative 5, right? So what I'm seeing here is that the general derivative, right, the nth derivative at x, and actually, I'm going to use the capital N plus 1 right now. Because remember, in that error term, that remainder term, I had the capital, the r, remember, I'll write it again, r sub n. Remember, this was the value of the n plus first derivative at some value of c, right, where this time c needs to be between 0 and 0.21, right, between x and a, divided by n plus 1 factorial times x minus, oh, this is x, right, because it's x minus 0 to the capital N plus 1. So I'll just write the general rule for capital N plus 1 right now. And I'm saying that we have this alternating going on. So again, I'll have negative 1 to a power. And I would like it so that for the odd derivatives, positive. For the even derivatives, negative. Now, this is going to be odd when capital N is even. So just negative 1 to the capital N. Right. When n is even, you have the odd derivative, and then negative 1 when even is a positive, right? When n is odd, this will be an even derivative, and negative 1 to an odd is negative, right? So negative 1 to the capital N, and that's going to go away anyway, right? This negative 1 power, because we're going to look at the absolute value, right? Absolute error. We're going to look at the absolute value of these things. Times, and then look at the factorials. Now the fifth derivative had 4 well, the 13 is in all of them first off, right? 13's in all of them. And then times, and then fifth derivative had 4 factorial, fourth derivative had 3 factorial, third derivative had 2 factorial, so it's 1 less factorial, so capital N factorial. So 1 less than the derivative factorial, and then times x plus 1 to a power that's just the opposite of the derivative here. So the opposite of capital N plus 1. So if I rewrite this, this will be a negative 1 to the capital N times 13 times n factorial, and then divided by, x plus 1 to the capital N plus 1 power. Now this, when I look at the absolute value of such a thing, right, because we're going to require that when we look at absolute error. I'll just get rid of this negative 1 to the nth thing, and then all this stuff here, except for x plus 1, x plus 1 could be negative, but, we're talking about values between 0 and 0.21. But anyway, this will be 13 n factorial times n factorial up top over the absolute value of x plus 1, to the n plus 1 down here. Now this is definitely a decreasing function. As x increases, the denominator would get huge, and the numerator, the denominator would get bigger, and the numerator is fixed. Numerator is a constant. Anything that's not x is fixed. So as x gets larger, this gets smaller. So this is a decreasing function, no matter what n is. And if you were if you were to look at it from 0 to 0.21, right, we're talking about that interval. If you were to look at it from 0 to 0.21, it's decreasing. So the value that's highest in this interval has got to be at 0. And when x equals 0 here, you just have 1 in the denominator. So the absolute value of the n plus first derivative at x is less than or equal to 13 times n factorial for values of x between, 0 and 0.21 for sure. Right. So I'm going to use that in our error. Right. And so that'll be for any value of c in here, right? This will be true. Because again, this is when x equals 0, you got 1 down here. Okay, so the absolute value of our error, after the nth polynomial is used to approximate the function, should be less than or equal to, 13 times n factorial over n plus 1 factorial times x to the n plus 1. And I can simplify this, and then we'll plug in our value of x, right? We're trying to approximate the value of this function when x is 0.21. So I'm going to put in 0.21 now. When we're approximating the function x equals 0.21, this should be less than or equal to, now n factorial over n plus 1 factorial, that's just n plus 1, 1 over n plus 1. And then times your 0.21 to the n plus 1 power. And they're trying to have us find, we want to find n so that this is less than 1,000th. All right. So once again, I'm going to go to a calculator here and enter this expression, change the values of n one at a time until we get a value, less than 1,000th, and then we're guaranteed that the error will be less than 1,000th. Right? And perhaps I'll even show that too when we look at our polynomials. Right. Right. So the expression I have is 13 times 0.21 to the capital N plus 1 power divided by capital N plus 1. And add a slider for n. Just change now when n equals 1, right? The error is going to be less than 0.286, right? It'll be less than this, but that's not less than 1,000th. And when n equals 2, that's not less than 1,000th. When n equals 3, that's not less than 1,000th. N equals 4, That's not less than 1,000th, right? When n equals 5. So you see how I wouldn't want to do this one at a time like they did with the first problem, because I'd have to keep repeating the process until I got out to the fifth n equals 5. I'd have to repeat the thing 5 times. But when n equals 5, you see this is definitely less than 1,000th. It's 0.0001. It's less than 0.001. Right? So when we use the fifth Maclaurin polynomial to estimate our value, the error will be no more than this. Right? So it should be good to the first 3 decimal places at least. Right? And let's actually see that happening. All right. So remember our function was this: f of x equals 13 times the natural log of x plus 1. And then what I'm going to do is put in we'll go to the 5th degree Maclaurin polynomial. All right. So the value of all these derivatives at 0. All right. So the original function at 0 would just be 0. Right. The original function at 0, natural log of 1 is 0. So that's 0. But the rest of them I got, right? So again, I'm just going to type these in. So 0 for the constant term. And the value of the first derivative at 0 is 13 times x to the first. And then the value of the second derivative at 0 would be negative 13, but then divided by 2 factorial, right, times x squared. And then the value of the third derivative at 0 would be 13 times 2, so plus 26. Then this is divided by 3 factorial, right, divided by 6 times x cubed. And the value of the fourth derivative at 0 would be just 26 times 3. Actually, remember I'm dividing each of these by, okay, so this will be a little easier actually. The fourth derivative is, negative 13 times 3 times 2, but I'm dividing by 4 factorial, so that'll get rid of the 3 times 2. So negative 13 fourths times x to the fourth. And then the fifth, finally, we're going on to the fifth Maclaurin polynomial at 0. It's 13 times 4 times 3 times 2, but divided by 5 factorial, we get rid of the 4 times 3 times 2. So plus 13 fifths, plus 13 fifths. Right. And actually, I could have made this 13 thirds here, right? 26 over 6, whatever, times x to the fifth. Oh, no. Oh, okay, I brought it back. Control Z, think I did it again. Control Z. All right, so sorry. I was afraid I was going to have to type all that again. Control Z is great. All right, so x to the fifth. All right, so you see how the fifth degree, look at this, right? Blue, green, blue, green, blue, green, blue, right? This polynomial near 0, near x near 0, 0 here is very, very close to the function. Now let's see what the value of f at 0.21 is, right? So there's 13 times the natural log of 1.21, 2.478 something. Now look at the polynomial at 0.21. It's the first 3 decimal places are correct. Like I said, right, the error should be no more than this. And 0, 0, 0 in the first 3. The first 3 decimal places should be correct, and we're seeing that here, 2.478. Yeah, but after all that, though, the answer is 5, right? We need to go out to the 5th Taylor polynomial to get an error less than 0.001 in our estimate. And again, they go through the explanation here. Oh, so this time they're doing it in general. The first problem, they did one step at a time. So I don't get it why, but whatever. Works out. All right. So one more. Hopefully just one more here. So this is suppose that you are estimating cosine of 0.3 using the third Maclaurin polynomial. So Maclaurin means, centered at 0. and the value of x is at 0.3. So we're looking at the interval from 0 to 0.3 for the cosine of x here, and then use Taylor's theorem for remainders to bound the error. So we did a problem like this earlier. They just want what's a bound on the error. When I use the third polynomial, Maclaurin polynomial, to estimate the cosine of 0.3, what's a bound on how far off that estimate would be? All right, so the function here is cosine of x. We're estimating or approximating the cosine of 0.3, right? So that's the value of x equals 0.3, with a Maclaurin polynomial. So a equals 0. And they want the third Maclaurin polynomial, P3. Right? So we're looking at R3, right? The remainder after the third polynomial should be equal to the fourth derivative, right? The value of the fourth derivative at some value of c, where c needs to be between 0 and 0.3, divided by 4 factorial, and then times just x minus 0 to the fourth, right? And we'll plug in, and we'll take the absolute value of this, the absolute error, plug in 0.3 for x. Now we saw before, right, the fourth derivative of sine is sine, and the fourth derivative of cosine is cosine again. And if you look at cosine x from 0 to 0.3, pi over 2 would be over here. Cosine of 0 is 1, and then it goes down to 0 at pi over 2, but we're only concerned with from 0 to 0.3, and the maximum this gets is at 1. All right, so the absolute value of this, right, so the absolute value of our error after and I'll just plug in 0.3 right now, will be less than or equal to, right? This fourth derivative here, the absolute value of it's going to be less than or equal to 1. So 1 over 4 factorial times, and then 0.3 to the fourth. So, and then whatever this value is, they want us to round it to 6 decimal places. Let's get rid of all this stuff from the previous problem. So 0.3 to the fourth power divided by 4 factorial is 24. And then rounded to 6 decimal places is 0.000338, right? Because the 7th decimal place is 5 or higher. So 0.00338. Now, again, it's starting with 0.00 here, so the error is not going to be bigger than this. That means that if we were to use the third Maclaurin polynomial, and plug in 0.3, we'd get an approximation of the cosine of 0.3 that would be accurate in these first 3 decimal places. All right. In fact, let me just show you that happening. All right, so f of x is cosine x. And then I'll put p of x, and we'll just go to the third Maclaurin polynomial for cosine x. Now that's everything evaluated at 0, so it'd be 1. Cosine of 0 is 1. The derivative is negative sine, that would be 0 at 0. So then I'm skipping that and then going to negative cosine, so minus, and then 1 over 2 times x squared. And then the third term would be 0. So you see that the second Maclaurin polynomial, and we saw this earlier too with the cosine function, the second Maclaurin polynomial is exactly the same as the third. Right? And look what happens when I plug in, 0.3. F of 0.3 So there's the cosine of 0.3. And here's our polynomial evaluated at 0.3, and you see how it's correct in the first three decimal places, 0.955. Right there, error is not bigger than this, 0.000338. But all they want is that error bound, that bound on the error. So the error will be no greater than 0.000338. Wonderful. All right. So that's it for that objective, right? You can probably see why I wanted to break these videos up. It's almost 2 hours here for just the one objective. So I'm done with this Taylor's theorem with remainder objective. So you'll see in the next coming days, the binomial series video, the functions expressed as Taylor series video. All right. And I already have the Taylor and Maclaurin cities video out. All right. All right. So done today, done with this, and hopefully this helps you out, right? And just remember, I said at the top of the video, the questions I saw here, right, may not be the same as the questions that you see when you work on it yourself, but hopefully they're close enough and the work I do is good enough to help you out when you work on them on your own. And thank you very much for watching.